Displacement. When we were doing the constant acceleration problems, how did we find displacement? You have the initial velocity, you have the final velocity.
You subtract them, right?
That gets you the change in velocity.
Oh, you
Either.
add them? No,
And then,
and then divide by 1/2.
okay, well, multiply times half or divide by 2. So that gets you average velocity, and then what? If you have average velocity, how do you find displacement? All right, flip back in the notes. I think Juliana's about to tell us unless something beats her to it. Yeah? Yeah. So close. Take the average velocity times time. This is very similar to the distance is equal to rate times time that you might have seen in middle school. So the change in velocity is just final minus initial because that's change. So that's FA. Oh, well, time cancels out, so that's going to go away. This is final velocity of A minus the initial velocity of A. Dot product with the average. And how do you find average? In general, how do you find average?
Take two numbers and divide it by 2.
Yeah. So saying here, if acceleration is constant, which we're assuming, you just take the initial and final values of the velocity, add them, divide by 2. So this is the initial A plus the final A divided by 2. So now we are left with, I need to explain dot products. Questions up to here before we actually talk about dot products? I have vector A and I have vector B. And I want to multiply them using a dot product. So I put a dot in between them. Well, if I'm multiplying, well, I can take any vector and break it up into perpendicular components. In other words, I'm going to break A up so that part of it is in the direction of B and part of it is perpendicular to B. So I have part of A that's in the direction of B and part of A that's perpendicular to B. When I'm doing a dot product, I multiply the parts that are parallel. So I'm going to multiply this part right here times the whole thing. Times all of B. So if, let's say that B is a vector 4 meters I hat. And A is 3 meters, or 3 newtons I hat minus 2 newtons J hat. So I can just sketch that out. I know that B is 4 meters in the I hat direction, so that would represent 4. That's B. And then A, I go 3 newtons in the I hat direction. Go for a different color there. 3 newtons. And then down 2 newtons for the J hat. So A is that vector right there. I just multiply the parts that are parallel to each other. So not going to worry about J, I'm just going to multiply the 4 times the 3. So A dot B is equal to just 12 Newton meters. One thing to notice is that the answer is not a vector. So dot products are also called scalar products. And then just for trivia, it's also called an inner product, but that's more trivia at this point. So dot products are scalar products. So when I multiply two vectors in a dot product, I get a non-vector. Cross product, we'll go into more detail later, but cross product, you multiply the perpendicular parts. And you do get a vector in the end. So the cross product, also known as a vector product, also known as an outer product. And you end up multiplying the perpendicular parts, whereas here you multiply the parallel parts. I'm going to do a 10-second aside. This is for those who've had trig. 10 seconds. A dot B is also the magnitude of A times the magnitude of B times the cosine of the angle between. All right, if you haven't had trig, don't worry about it. That's just an aside for those who've had it. So if I take a vector and I do a dot product with itself, so if I take my vector A and the dot product with itself, what do I end up with? Or if you want something more specific, over there, if I had 3 I hat dot 3 I hat, so any vector times itself, what do I get?
3 I hat squared. Or would it just be 9?
Just 9.
Just 9.
So any vector dot product with itself is just whatever the magnitude of the vector is squared. And one other piece of information is that the order does not matter with a dot product. That A dot B is the same as B dot A. Order does not matter. Math terminology, the commutative property holds. Questions up to here, because we're about to apply this. All right, so I got this thing, this vector dot product with another vector. I'm going to FOIL. I assume FOIL is a familiar term, or at least somewhere in the back of your mind you remember FOIL.
It's
Not
been a long
any
time.
sense. Okay, got one person who remembers seeing it before. The half right there, I'm just going to bring that out front. Divided by 2, so it's multiplied by half, so I got a 1/2 in A. All right, so FOIL, basically you multiply the first terms. So I'm left with VFA dot VIA. Then outer, so first, then I multiply the outer ones, VFA, so plus VFA dot VFA. Inner minus VIA dot VIA. And then last, that's the FOIL, minus VIA dot VFA. If you remember distribution, this is just basically an extra step in distribution. Well, let's see what we got here. I got VF times VI minus VI times VF. The order doesn't matter, so those cancel out. So that cancels out with that. Here I have a vector doing a dot product with itself, so that's just VF squared. And then here, I got, again, a vector dot product with itself minus VIA squared. If I distribute, I have 1/2 MAVFA squared minus 1/2 MAVIA squared. So that's where the 1/2 MV squared comes from. And I suspect some of you are thinking, hey, that's great, wow. But, so what? What does this tell us? Questions up to here before I actually talk about what this means and why this has any importance whatsoever. Since I have F equals MA here, this has to be the total force. This is the total force acting on A. So that is the total force times the displacement. Physics people cannot settle for just leaving it at that. They have to give it a name, and they call this work. It is the total work, because it's the total force. So the total work, you work your way through this and you end up with this. The total work is this 1/2 MV final squared minus 1/2 MV initial squared. So whatever 1/2 MV squared is, it's the final minus initial, so it's just the change. It's the change in this 1/2 MV squared. And of course, they can't be satisfied with just saying 1/2 MV squared, they have to give it a name. That 1/2 MV squared is kinetic energy. Cleverly labeled, symbolized by a capital K. So the total work acting on an object is equal to the final kinetic energy minus the initial kinetic energy, or just change in kinetic energy. This is known as the work energy theorem. I got the word out there. I said it correctly, I just wrote it wrong. Work energy theorem. Personally, I don't think it's a theorem. It's true because we define work and kinetic energy as such, but I was not part of the selection committee before I was born. So before, when we were looking at 1/2 MV squared in those problems, we were looking at the kinetic energy. The total kinetic energy beforehand was 94, afterwards was 274. We gained kinetic energy. And the only way you gain kinetic energy is if you have some outside influence. There has to be doing something. The only way a system would gain kinetic energy is with some outside system, outside force. In other words, it's not a closed system. Sorry, should I? Now, the fact that kinetic energy equals 1/2 MV squared, I'm going to write that in big print. Is that important? Matter of fact, we will. Kinetic energy. So later on, if I ask you, what is the formula for kinetic energy? The proper response is 1/2 MV squared. I want you to know this formula. 30 years from now, we run across each other in the street. You look familiar to each other. We start talking about how we know each other. We eventually realize that you are a student in this class. I should be able to ask you, what is the formula for kinetic energy? And you should know it.
Oh, good, right away.
So, if I say, what's the formula for kinetic energy? The proper response is 1/2 mv squared. It's not 1/2 times mass times the speed squared, even though it is, but I just want 1/2 mv squared. And I am serious about the next part. I'm about to ask you that question, what's the formula for kinetic energy? And everyone, in unison, I want you to reply 1/2 mv squared. The chorus of angels. Here we go. What's the formula for kinetic energy?
1/2 mv squared.
Oh, that was nice. I will ask you that throughout the course, the remainder of the course. All right, so energy. Physicists like to come up with rules, you know, some simple rule. They have conservation of momentum, they want a conservation of energy rule. Trouble is, yeah, I can make the claim that there's conservation of energy, that right now this has no kinetic energy because it's at rest. I can push on it, it gained kinetic energy, and then it stopped again. And you just have to trust that whatever energy was lost can be explained. So they wanted to come up with something a little bit better than that. So they decided to come up with different types of forces. Marker slides here. There are conservative forces. And if it's not conservative, liberal is not the answer. It's non-conservative. Now, there is an official definition, which I don't think is very helpful here. So I'm just going to list out all the conservative forces we've dealt with so far. Done. That's the only conservative force we've dealt with up to now.
What's under force? Right.
Weight.
Wait.
Weight is being a specific case. Non-conservative forces, everything else we've done so far. So tension, friction is the classic. Normal. All right, little vocab time here. Why do you suppose it's called a conservative force? What's being conserved?
Weight.
Not the weight being conserved.
Energy.
Yes. Conservative forces conserve energy. So, a conservative force will changes energy from one form to another. There's more than just kinetic energy. There's three types. Non-conservative force does not conserve energy. It transfers energy from one object to another. be much better. So when I pushed on the box, I pushed on with a normal, applied a normal force. It's a non-conservative force. I transferred the energy from my hand into the box. It slid for a bit, it stopped. Friction, a non-conservative force, took the energy from the box and it transferred it into the table. And the table heated up a little bit. So if conservative forces change it from one form to another, what are the other forms? We've got kinetic energy. What else is there? I'm sure some of you have been exposed to this in the past. What's the other type of energy?
Potential.
Say it again?
Potential.
Indeed. So we have the types of forms. We have kinetic and potential. That's it. And the third kind is rest. Rest energy, most of you know the formula, although if I said write down the formula for rest energy, most of you would go, what? But you know it. I will start out. E equals
MC squared.
the formula for rest energy. M sub 0, C squared. And this M sub 0 here means the rest mass. When you have found the mass of objects in lab, that's the rest mass. All right, need some space here. Any questions before I erase this?